Welcome to our product pitch for the Mars EEV. My name is Ayan Sharma and I'm here with my colleagues for this presentation. So we'll begin with the actual deliverable for this project, which is a EEV vehicle which is capable of traversing Martian moons Phobos and Deimos. It's able to carry 2 crew members as well as retrieve a sample of 50 kgs which is brought back to the Earth. The overall purpose or the importance of this mission is to quantify water deposits as well with core samples that we're bringing back to the Earth, as well as to quantify the actual existence or the submartial water deposits that are available within the Martian moons itself. Next, we'll talk about you, the stakeholders, and the big picture of the projects 2 years to come. The primary stakeholders, of course, the investors and the government agencies such as the US, Russia, China, India, and other that are driving these missions to different planets and the Martian moon itself. The potential resources and motives for these missions are primarily one we already talked about, is actually establishing the science that we got through information through the MMROs and other things like that to establish that the ice core samples actually exist within these vehicles. Also establishing assets near the Martian surface where astronauts can build and test subsystems for future solar system adventures. Go. The main purpose of the whole rover itself is to drill ice core samples. And right now I'm going to talk about the Trident drill system that has been employed by the Viper rover and is part of the 2024 Lunar Discovery Program. The drill itself is capable of drilling through icy materials up to depths of 1 to 3 meters. It also shows that within the slide that the picture on the left shows a detailed view of the process and the drilling process, as well as to the right we can see how the actually mechanism takes and locks in to commence drilling. The next slide shows the actual sketch of the EEV. The main components include wheels, which have little grooves and different components that ensure better mobility and restrict the vehicle from being stuck, as well as the Trident drill, which we already talked about in the previous slides. And finally, we have the chassis, which is designed to be optimized for maneuverability to travel across different terrains and craters within the Martian moon surfaces.
Hey everyone, my name is Garrett. So essentially, once we had defined our problem, we'd set our goals, and we'd also set our reasoning for why we wanted to go to Phobos and Deimos. We essentially wanted to do a few trade studies on different subsystems of our rover. Just kind of a few examples being such as like the rover material, a spectrometer subsystem, a suspension system, and also like a communication system. From there, we determined that the most important trade study we would do would be the spectrometer, as of course our main purpose is to go and do research. So we want our research equipment to be essentially top-notch, so our mission won't fail. We evaluated the spectrometer on a few different criteria, such as being the wavelength resolution. That way we could like study the absorption, hydrous minerals in the different samples, the signal-to-noise ratio, reliability, so that way our system doesn't fail too often, the amount of power that the spectrometer uses, and also the portability, as of course with more weight it becomes more costly to actually send the rocket into space. We evaluated a few alternative trade studies going from like LiDAR, Tingo, CMDM, Sherlock Pixel, kind of just varying between I guess like laser evaluation and then just like dust sampling. And from there we actually did a topsis review and examined each spectrometer given its different evaluation criteria, and we determined that our Sherlock spectrometer would actually be the best option to send on this mission.
Hey guys, my name is Will. Today we'll be talking about concept architectures and different parametric modeling techniques for our different systems. For our space system, we split it up into the left for 2 different starts for launch and prepare ground and comms, which are furthermore broken down into something that we generally kind of see inside of more general documents such as launch stations, fuel, orbit station mixing, and transmitter radio styles. And on our right, we have our space systems for our rover and logistics. We have received transmission and EMF load lines along with things such as our dates and plants and refueling, along with a sample station. Now, when we have those functionalities that we discussed earlier, we're going to have constraints that are developed off of those types of functionalities, where we have things such as money costs, temperatures, day-night cycles, and other types of interferences that could get into our system that are going to be illuminated and exasperated. So, off of those constraints, we could then hop into kind of organizing our thoughts together and getting our general constraints for our requirements. So on the left, again, costs. On the radio and launch, more different requirements that we discussed about our functionalities and such. And our rover, spectrometer, and bases are all requirements that are put into our fancy little 80-page document. For our Gantt chart, we go ahead, organize all our events and timelines onto a kind of organized statement of where we're going to be at a certain time lapse. So we have things such as our receive and transmit boards, spectrometers, and other technical equipment types, along with funding and general seeds. From there, while we're on the ground and do all of this while we're actually building the rocket, we then move on to our space systems, which look like so on our timeline. Notice how now, instead of using the ground and launch systems, we now use our space systems for diagnostic checks, communication checks, landing and reciprocation, and etc. that you would generally expect in spaceflight travel. Alright,